Many open source projects can begin as sort of side projects, but foundational mathematical software can require a lot of depth and persistence and like of a research program. So developing these kind of systems involves a lot of years of work, often without any kind of support available to normal researchers, because it's entering new concepts that haven't been explored in a particular way before. So working independently for so long has been challenging, but has allowed me to pursue ideas that might not otherwise be developed. So that's what my project does. It has developed a lot of mathematical concepts into software that otherwise wouldn't be done in other contexts. And because of persisting with it for a long time, it's developed into a coherent framework over time. So what I've done is I've published a book in 2025, which helps explain the general research program behind my software and the sort of ways you can interact with it in a basic way. So I had to write a whole book to do all that. I just was accumulating different information into my PDF document, and it ended up being a over 500 page book when it all came together, and I had to stop at some point to get it out there. So this was the point at which I decided I need to get this out there. So I published it at that time, and I would appreciate if at this time people would take a look at it and see if they want to buy it, because it's a pretty good book. It's not perfect yet, but I think at it was the right time to publish it at that time. So it's a good point in time of where my project was. So that's why I published it as this, and I didn't give it a low price because it's supposed to support my project as well. So I would normally have wanted to make this a low priced book, but because this is specifically meant to support my project, it's priced like an academic book. So that's why it has those kind of prices. So I hope that people might be interested in supporting it, and I'm going to explain more about what my project is about. So mathematical language and computation are essential for 21st century science and engineering. And common mathematical software is missing many of the foundational concepts that can be exploited from the literature, for example. So my goal was to implement deeper mathematical structures directly into computational language design. So I made a rigorous effort to reimagine the foundation of computational math with underutilized concepts. So there's a lack of established funding for this particular endeavor, and continued progress requires dedicated support and funding, I would say. So especially in 2026, where price of computers is pretty high already. So yeah, so that's why I've also made this book available. There's a paperback and a hardcover version as well. So there are two different versions of the same book. Yeah, and so that's to help. So that way, if you want to support my project, you can actually get something in your hands in return for supporting it as well. But there are, you can find other ways to sponsor this project on GitHub. There are various ways GitHub and I guess Patreon and other websites can do sponsorships or whatever. So the existing mathematical software typically lacks a more unified mathematical foundation, and more advanced concepts from algebra and calculus often don't make it into engineering software. So due to the inertia of mathematical knowledge mainly, because you can't necessarily expect everyone to have a full comprehensive background of all the necessary mathematical concepts that could go into a software like this without spending a lot of years on it. So I decided I would spend the time to make the kind of software, different kind of a software. So and now the first book on this particular type of new approach has been of my particular approach has been written. So that should help overcome some of these limitations with the software developments demonstrated in my projects. So the result of this work are the highly useful tools, which are far ahead of their time in terms of adoption by engineers and scientists and so on. So bridging the gap between this new software and the scientists and engineers requires funding and support to organize useful work around it. It doesn't just magically happen by itself in the world that we live in. Once the software matures and people comprehend the new approach, many different applied sciences can more easily share a unified foundation. So a more unified foundation for applied sciences makes solving adjacent problems in different fields of research more natural. So Grassmann.jl is the primary project that I'm talking about, or that everything's built on for this. It's a computational language design for geometric algebra and exterior algebra. It's named after Hermann Grassmann, which is a mathematician who developed originally developed a lot of these concepts about geometric algebra, like an algebra of space, a multilinear algebra, basically. So that was refined by different people over time, including Clifford and Hodge and different other mathematicians, including Hestenes more recently, and many other people. So, but it's not like it wasn't in the mainstream academic textbooks though. So it was kind of like wasn't the mainstream thing, even though it had been existing the whole time. And yeah, it enables calculations involving multivectors, Clifford algebras, differential forms, geometric transformations, and so forth. So let's take a look at the README. Yeah, so this is basically something kind of like a computer algebra package for doing numerical calculations with geometric algebra objects. And this, it can handle symbolic computations as well in different approaches, but the primary idea is to do numerical calculations with this software because it's been specifically written in a way that when it compiles, the code is generated for numerical computation. There would have been other approaches better optimized for symbolic computation, but this, it's not that you can't, you can do symbolic computations as well with some of this, but it's more about the numerical computation side of things in this project specifically. So it can, create, has a lot of data structures that this defines for these algebraic objects, and it has to define the algebraic operations between all these different data objects. So there begins to be a combinatorial explosion of different type of mathematical objects that have to be able to be operated on and combined algebraically. So, and because some of these different algebraic objects have different, can be represented with different structures, that means that they can be optimized in different ways, and because, and then there's this combinatorial interaction between different types of objects that each one can have it, each combinatorial combination can each combination can have its own type of optimization applied to it. So it begins, so there's a lot going on that at the surface everything can be thought of as a multi-vector, but when you break it down into many different other types of things it could be, there's this combinatorial explosion of different types of objects, and the way they can interact in unique ways can all be optimized depending on what types of objects they are. So I've kind of tried to draw like a fine balance between how many different types of objects I have and how they interact with each other and so on. So I've kind of settled on this design. This is the design that I believe would be good for what I'm trying to do. So I've thought about like expanding it in different ways and changing it around, and this is what I've settled on at the moment. So this, and I think it's going to stay settled like this for a while, which is why I was ready to publish my book about it. So it took me a long time to publish this book because I wanted to settle down on what I was doing here. I didn't want to be, because there were some things I was changing up still. And I didn't want to be, constantly be worrying about that I already published this book, but I'm still changing things around. So that's why for many years I didn't have like a book to help fund my project yet. But now the project is past a threshold where I already published this book and it's settled down to these kind of definitions that I'm working with. So yeah, that's the Grassmann.jl project that I developed. And then I have, a bunch of other projects as well that I develop, and one of those is the Cartan.jl project. So this is another one. This one builds on the Grassmann.jl project itself, and it's for doing calculus with it, basically. So in multilinear algebra, and then doing calculus. So it introduces the unified numerical framework for the differential geometric algebra that I want to study. And it has been purpose-built for the formulation and solution of partial differential equations on manifolds with a non-trivial topological structure. And we'd like to use the Grassmann.jl algebra for all the things we're doing. So this was written in the Julia language, uses differential geometry, geometric algebra, tensor calculus, support for the fiber product topology, which enables directly executable generalized treatment of geometric PDEs over grids, meshes, and simplicial decomposition. So this is a system that supports the intrinsic formulation of differential operators like the exterior derivative, codifferential, the Lie derivative, interior products, and the Hodge complement. And using this coordinate-free algebraic language that was grounded in the Grassmann-Cartan multivector theory, its core architecture accommodates the numerical representation of principal G-fiber bundles, product manifolds, and submanifold immersion, providing native support for PDE models defined unstructured or unstructured domains. So Cartan.jl integrates naturally with the simplex-based finite element exterior calculus, allowing for geometrical discretizations of the field theories and conservation laws. With its synthesis of symbolic abstraction and numerical execution, Cartan.jl empowers researchers to develop PDE models that are simultaneously founded in differential geometry, algebraically consistent, and computationally expressive, opening new directions for scientific computing at the interface of geometry, algebra, and analysis. So that's kind of the main summary of this, and this again defines a few, definitions and objects and methods to operate on those objects, which I have settled on over time. I've been refining my idea of how to approach this, and this is what I decided is a good way to move forward, and it's discussed in my book as well. So my book is called Principal Differential Geometric Algebra, Compute Using Grassmann.jl and Cartan.jl, which are the two software packages which are open source, which I explain to you right now. And so we can read the summary from the book here. Principal Differential Geometric Algebra is the first reference of its kind, built on rigorous category theory foundations and a full unified TensorField computational language design for differential geometry. This category theory foundation presented is a custom-designed formalism for categories to specifically emphasize the existence of choice morphisms relevant to mathematicians interested in how axiom of choice appears in class and set theory. Next, the book introduces essentials of geometric algebra as the primary basis for differential geometric algebra computational language design, using the Grassmann.jl library for Julia language. Developed completely from scratch, Grassmann.jl introduced many new pioneering computational language designs to enable reproducible scientific research with numerical differential geometric algebra. Building on Grassmann.jl, the Cartan.jl package is the first computational language design to pioneer a FrameBundle for the PrincipalFiber G-bundle formalism used in advanced differential geometry. Not only does Cartan.jl present a completely new programming paradigm for working with an abstract FiberBundle topology using numerical analysis, It also unifies the topological implementations of structured and unstructured finite element methods, and also spectral element methods. This book emphasizes the analysis of eigen-characteristics with multilinear algebra, differential geometry, and partial differential equations. Many figures and diagrams are included, all scientifically reproducible with concise programming language. Partial differential equation examples are evaluated with boundary conditions found in the literature to help scientists and engineers validate the usefulness of the computational language design. Also included are many special and elliptic functions and appendices for basics of the Julia language. The Reduce.jl package, the Fatou.jl package, and the new Unified System of Quantities for physics units from UnitSystems.jl. So that's kind of the main summary of what's going on in my book. Is this clickable? No. So that was a summary of the book. So we can just kind of summarize this one more time. So it does talk about category theory at the beginning of the book, and this is actually a custom formalism for category theory I introduced in my book, where I emphasize the axiom of choice in how it would show up when you're talking about morphisms in a category, right? So I thought that was something I wanted to clarify for myself. So I studied that, and so now I'm making that what I studied available in my book there about category theory in the first chapter. So then the rest of my book, aside from the set theory part at the beginning as well, talks about using the Julia language to use to calculate with my software, Grassmann.jl and Cartan.jl. It develops kind of systematically all of mathematics, well, not all of mathematics, but the mathematics that's involved in this book. It is built up from category theory up to learning it introduces real numbers and arrays or vectors, and then geometric algebra, and then calculus and so on. It's not the most complete text on all these topics individually, but as a whole, this is the first time you can go from category theory to partial differential equations and geometric algebra, all in a single textbook that has programming language examples as well that are scientifically reproducible and all that. So it is kind of a first of its kind in that sense, that it does all those things together in a single book. And some of the ideas in the book are new as well in terms of that some of the different concepts I have, but a lot of it's of course based on the existing. It's made to resonate extremely well with the existing historical literature on all these topics, which is a vast historical literature. It's a lot of different people have discussed all these topics before, but it wasn't the mainstream mathematics necessarily, but there were a lot of people discussing it before, and this is my take on all this in terms of writing software for it. So such a project requires years of rigorous step-by-step research and development. And while substantial progress has already been achieved by this project, a better effort requires more support and collaboration. And since this is advanced math software, advanced mathematics, it requires lots of time and deep domain knowledge to implement, maintain, and document. So the documentation itself ends up being kind of a textbook writing exercise, which is, as you've seen, I've written a textbook about this now as the documentation, basically. So that's, I guess, the direction that a project like this ends up going. So more funding would promote more features, more documentation, more collaboration, more tutorials, more applications, a more coherent ecosystem, and so on. And there are countless science and engineering problems that can be tackled, provided that there's adequate funding to do the work, and more mathematical structures that at first appear separate can be unified if the effort can be dedicated towards it. And yeah, like specifically partial differential equations is a topic that I want to address with this software. So that's why the book ends on that topic, basically in the last chapter, because that's kind of the research topic that it leads to for me personally. There are, other kinds of things, different approaches that people can take. This is so in my project, what I am reaching towards is studying partial differential equations at the end of the book, basically. So that's what it looks like for me in this book. So the benefit for supporting such a project is universal for researchers, universities, engineers, physicists, scientists, students, and so forth. And this not only supports a mere software library, but the development of mathematical infrastructure for scientific reproducibility, which is something that matters in 2026, especially since we are interested in having scientifically reproducible research when it comes to mathematical concepts. I mean, people always wanted to do that in mathematics, but still in 2026, we still want to do that, right? So that's the state of things as far as that goes. So due to the generality of this computational language, these methods can quickly compound and build an already existing unified foundation. And I already spent many years on this. I already reached the point where I wrote the book about this. And so it's already reached a point where it can now quickly compound and build on already existing unified foundations. For example, it becomes easier to transition a problem from one or two dimensions to a higher dimension without re-deriving it for each situation, because a lot of different methods have already been implemented here that allow that when you solve a problem in one or two dimensions, you can now easily do it in any number of dimensions, basically. That's what this kind of software helps me do, at least. So what you can do is you can also start this project on GitHub, also on Codeberg. I also have a Codeberg. On Codeberg, they recently changed their terms of use, saying that the LLM generated content is being restricted. But for me, this isn't a problem for my specific project, because I didn't use LLM generated code in my project. I'm always typing everything from scratch in my project. So that doesn't mean I think AI can't ever be used for anything. That's not what I'm saying. But for the actual programming itself that I do, it's never an issue about how fast it is to type what I want to do, right? So I've manually written everything. Everything in my project is manually typed with my own fingers, always. there's never a time where I don't manually type the code in my source code, basically. So I do, sometimes ask an AI if or LLM if some of the naming conventions are appropriate or not, because there could be ambiguities that I may not fully understand or be aware of. So I find it useful that a language model could help me figure out if there's an issue with the choice of what words I'm using, for example, but not the actual code that I generate. And that's always written by hand. It's just like philosophical, like having a chat with somebody, like if I about whether I would use a particular word in a certain context or not. That's probably that's how I would describe my use of an LLM, basically. But uh, yeah, so because for my project, even I don't even use find and replace very often. If I want to find and replace something in my source code, I often do it by hand. I don't do it. I could, do some kind of, sometimes, depending on what it is, you can use the find and replace command in your text editor. But oftentimes I'll actually manually find and replace each instance so that I review the code in my project and check just check the context of each find and replace so that I know what's going on in my project. I like to be that involved in my source code. It's not because find and replace, yeah, it would be faster and a lot of times to use that command. But then if I don't manually go through each line of code and look at it, I'm not as familiar with my code base, right? So I actually am fully familiar with my code base that I go through line by line if I want to sometimes make changes like find and replace. That's how I do it. So, and it's not the problem for me that it takes a long time because I'm processing a lot of mathematical concepts in my mind. So I can do some text editing while I'm thinking about mathematical concepts, right? So I might go through by line through my project at the same time I'm kind of mulling over some other concept about what I'm trying to accomplish. So that's kind of how I work. I think this. So yeah, my project is on Codeberg as well, which doesn't allow LLM generate content, but for me that's not an issue because I'm not saying other. I don't know. For me, that's just how I do it. So I happen to fit on the Codeberg website, and yeah. Um, so you can start my projects on GitHub. You can buy my book here. So it has a lot of stars on GitHub, and a lot of people follow me on GitHub. Uh, there we go. So recently there was this website made. Oh, let me turn on this. This website that was made, which is pretty cool. This shows my profile on this website, gitfoot.com, which I don't know. I just think it's a kind of a funny, silly website. What is this trophy cabinet? Awards earned, Golden Boot, the season's top scorer, held not kept, awarded on current form to finishers whose repositories keep hitting the net. Okay. So, I guess, yeah, it says Hall of Fame maintainer. So, I don't know. But yeah, I'm not the most popular person on GitHub for sure, but I have been on here for I've been on GitHub for a long time. So, yeah, yeah, so mathematical advancement always required the creation of new language frameworks. And this is an attempt to better facilitate computation for humans, basically, right? So we need computational language to interact with the computer for these mathematical things, right? So somebody has to write the computer program that calculates these things and provides a language for humans to interact with it, and that's the sort of thing that that this project does. Some of my other videos, might talk more about code examples and animations of things and diagrams or equations or demonstrations of things. I think I've already talked quite a bit for this video. I don't know if I should keep making this longer and longer. Probably it's already been going on for quite a bit. But by working on this project, I have absorbed a lot of financial hit for many years, with not a lot of reward for several years of that. But I did, finish writing this book in 2025, so people could support it that way and get something for themselves as well at the same time by having the book and learning from it. But yeah, so that's my project. It'd be cool if I guess people would check this out or whatever. So thank you for taking a look.
Cross product of two things that are parallel is zero. So there's no force on a field aligned current. So the superimposition of the circular component with the linear component, or an arbitrary angle of input of current, is of course circle plus straight lines field. Now, why they form in pairs is not an easy question. They do. That's a laboratory finding. The little curve on the right just shows that if these things get too far apart, there seems to be a force to pull them back together. If they get too close together, there's a force that pushes them apart. Plasma forms cells. It insulates regions of plasma, nearby regions of plasma, just like blood does. So simple electrostatic analyses usually fail. Pratt did these simulations of plasma and actually was able to create something that looks like a spiral galaxy in a computer simulation in a supercomputer. Who was able to create in actuality in the laboratory a plasma structure that looked exactly like a large spiral galaxy. The profiles that Pratt's simulations predicted and the profiles that Bostic's models produced exactly what